Wireless LAN Professionals Podcast, episode 130.
Wireless LAN Professionals is a place to educate, inform, encourage, and entertain those involved in wireless LANs. This Wireless LAN Professionals podcast is an audio manifestation of these goals. Our host is a wireless LAN veteran, consultant, designer, and teacher, Keith Parsons. And now, the podcast for wireless LAN professionals by wireless LAN professionals.
Glenn, how are you?
Keith, I'm doing great. How are you doing today?
Not bad, not bad. We are communicating over the interwebs in 2 different countries, 2 different continents, way 2 different time zones, and yet here we are talking together.
Yeah, it's pretty cool. It's neat how this technology actually works, isn't it?
And when it does, we're just happy as can be. We had a chance a couple weeks ago to be in Orlando together at Wi-Fi Trek. You were presenting, I was presenting, and I thought we could share about your presentation with our podcast audience. You good with that?
I'm really great with that. Yeah, it was a lot of fun, great presenters, and Wi-Fi Trek was just an awesome experience, and can't say enough about it. Really thankful what CW&P is doing to bring these presentations out to us.
And I'm not saying they did it because we did it first, but they had all the presentations live. They were recorded this time around, and they posted them up very quickly after the conference is over so everyone can share. I'm a believer in sharing knowledge, so kudos to CWP for getting those out.
Yep.
Well, what was your topic?
Well, Keith kind of had Tom Carpenter mentioned, kind of a corny topic. My topic was about teach me to fish, and I will teach you about data rates. And I had a fishing story to start and a fishing story to end, and learned a lot about fishing, and helped me learn a lot about data rates as well.
Well, I like the data rate parts, not so much the fishing part, but that's not because of your story. It was a good story. I've been punished by my wife for too many years. Fishing is a selfish act because you leave the children with her, and thus it's not a good thing to do on a weekend. Totally has nothing to do with what we're talking about. So let's move on. So let's skip the fishing story and jump right in. How did you go about researching your presentation on data rates?
Yeah. Well, the fishing story actually kind of kicked off things because I realized I needed someone to mentor me, just like a friend of mine years ago needed to be mentoring him about fishing. And I thought I knew about data rates. You know, I'm CWNE as well as you, and had a lot of questions that came up on my Slack group and some Twitter feeds. And all this sort of I can't answer all these questions about data rates. So I wanted to get some mentor input. And I prepared a list of questions and sent them out to a number of WLAN professionals, you being one of them, and you had some great feedback. And I wanted to get some information from WLAN professionals out in the field, out in the trenches, if you will, and really learn more about data rates. And so that's what I did, put that together, and that's how the presentation kind of came out.
So how many people were in your mentor group? You're the mentee, they're the mentors, yes.
Yeah, well, some was interesting. That some of them actually responded. Some of them responded through my website that I have, my blog site. Some of them just hit me up on my Slack group. I put a question out there as well. And so I had about 30 people altogether responded. So I had a good feedback and a lot of great input from these men and women who, like I said, they're in the trenches. They're using data rates day in and day out, and really helped me a lot.
One of the questions I like a lot, in fact, it just came up with a conversation I had with another professional today, and they said, almost verbatim, one of your slides, it said, would it be great if all clients and APs talk to each other at the highest possible data rates? And their question was, how come they don't? So,
yeah, it's a good
short little question, but has a really big answer.
Yeah. It's why don't they talk together? We wish they would. If you had one client per AP, I think everything would be wonderful. But we don't. We have everything from code channel interference, from not having good channel reuse, to RF interference, to too many clients, and again, causing interference and too much congestion, if you will, on the band. And a lot of the different WLAN professionals who are responding to me mentioned many of the same things. We just don't have a perfect world. We have sometimes low data rates are enabled, which cause some clients to actually hog the airtime. And just a number of different reasons. Yes, if our data went over the air at high rates, we would have great Wi-Fi networks. But in real life, it doesn't always work that way.
Another thing in real life I've noticed through packet captures, it's rare if ever, depending on the trace file, that your client transmit data rate is the same as your access point transmit data rate. That they are ever matched is like, oh, look at the two matched for a while. And so it's not a synchronized event. Data rate up and data rate down most of the time are two separate things.
Yeah, I noticed that as well. I did some packet captures at work, and just I won't say they were all over the board. I mean, generally, you do know that the management and control frames are set at lower rates, and that just so all stations can hear them. And then the data frames are set at higher rates because, well, we want higher rates because it's data.
Hopefully they're at higher.
Yeah, sometimes they're not, but. Yeah, I noticed, and I think it just really depends on that secret sauce algorithm, the way dynamic rate shifting works. The transmitter makes that decision, we're going to transmit at this data rate, and if the receiving station acts that frame, then we know, hey, that went through well. And if it doesn't, it changes. And then when it goes back, when the receiver or the client now is the transmitter and the AP is the receiver, it often goes at a different frame rate. Why that happens, again, I think it's part of the secret sauce that's in the client and also in the access point software, possibly some of the silicone in the chipset as well. But I did notice doing some captures that, nope, they're not the same. It'd be nice if they were, but they're not.
Well, and it's part of the reason they're not is they have different capabilities. One, different silicon, different chips. But they also have different antennas, different distances. They might be receiving multipath entirely differently. So, yeah. Big changes. The other thing I think people don't realize on this data rate issue, and one of the tools I just love to show off is Adrian Granados's Wi-Fi signal. I have it up on my screen all the time, and I have it plotting MCS data rate, and you can actually watch. Like right now, I happen to be switching between MCS 7 and MCS 6. I'm not moving. The access point's obviously not moving. And yet it's making a decision to change modulation because it, as a transmitter, can't maintain it. So part of the deal is the transmitter is the one that makes the decision, not the receiver.
Yeah, that as well as I had one of my mentors who I think had a little cracked door into one of the vendors. He said that what he has noticed, at least, that the modulation and coding rate and sometimes even the channel width will change depending on how the access point and the client communicate with each other to try to keep that client as solid as possible of a connection. And I thought that was interesting. So as much as we think, we know, we're like you said, we're not moving. And so what exactly is that access point thinking? What is that client thinking? And it's really detailed information. And yet we can, as you said, Adrian Granado's Wi-Fi signal, boy, I have it up as well. And I love to watch it and just to see what's happening.
And you can just plot it right out. Well, I think part of if you look at a MCS chart, what's going to happen is when you negotiate the first association, you're at the highest possible data rate that's supported by both client and AP. The client has to remember all of its choices to its AP, but the AP has to remember all clients, all choices. So it's going to have a table for every possible client. And then they'll work through the table. Now, the process of going up, down, left, right, diagonal through the table, that's the secret sauce. And yet, I've seen some do this really weird thing. And you say, let's just pick a random one, MCS 9 on a 2-stream, 80 megahertz wide. That's 866. And so it starts at 866 because both the client and the AP support it. And then when it fails, instead of just climbing straight up by changing modulation or changing coding, this client jumps all the way to BPSK 20 megahertz. Boom, all the way down to 6.5. That's a huge leap from 866 down. But I think what they're doing, and having watched this a couple times, the client is choosing to say, rather than waste time slowing down, trying, maybe I'm not within range of the AP anymore. So let's try the worst possible, most resilient modulation, the coding scheme that has 2, and I only get to keep 1, so it's 100% packet extra coverage. And if we can't do 6.5 BPSK, let's roam. So it's a faster technique to get to roaming. It slows down the network when it does it, and then it slowly builds its speed back up. Some go up, some go diagonal, some change 80-40-20 and then climb. I've seen a wide variety of behaviors in that DRS that you talked about.
Right. And that's and one thing I found out through some of my mentors who helped me out with this presentation was DRS is the same DRS works for every PHY. And I don't know as much about AX, but I'm pretty sure DRS is going to work with AX as well. And it's great to see that technology really work out. One of the things as I was looking at dynamic rate shifting, I did see that there's this little, if you will, little caveat in the 802.11 standard that says the transfer of information about dynamic rate shifting is not part of the standard. So it is up to the vendors. It is up to the chipset manufacturers on how the DRS algorithm actually works.
And they do it pretty fancy different ways. That's kind of what they're good for. But here we are on the other end trying to make our networks be as stable as possible. So one of the comments I have a bit about DRS is it's the part that makes Wi-Fi complaints increase more and more because people go, Wi-Fi is slow. Well, actually, Wi-Fi slowing down is part of the protocol. It's designed to slow down. It's designed to say, I care more about staying connected than about speed. And so when our customers say, oh, the Wi-Fi is slow, you should jump up and down and yell and scream and say, yes, it's doing exactly what it was programmed to do.
It's so resilient, Keith. As we know that as your signal strength it gets weaker, you use a less complex modulation encoding. And the 802.11 standard is designed that way so that you can ensure the integrity of that packet or that frame as it gets across. Then as you get stronger signals, you can use the more robust coding and modulation schemes so that they can transfer that information at a stronger rate. So, yeah, exactly. Wi-Fi is designed that way so we have good signal integrity.
And we also have the whole dynamic piece. I don't even know if it falls in the code as DRS, but as we have spatial streams, when we have 3, we can use it. We have 2, we have 1, and that dynamically changes all the time as well. And those are pretty big jumps when you change spatial streams. Yeah,
one thing that I noticed that why some people also complain, well, why is my device not working as fast as the access point? The access point maybe is 3 spatial stream device, whereas my access or my client is only a 1 or 2 spatial stream device. So your devices also cannot leverage all the things that access points can provide. And so they can do the best they can, but they can't create another spatial stream.
Or they can't support it because the chip doesn't do it. I think one of the best resources available is Andrew Van Aj's spreadsheet. And if you really want to get in, it's a capacity planner. But if you want to understand data rates and how these rate shifting things work, just reverse engineer Andrew's spreadsheet. It's all available for you to go and look and see in the cells. Now, you can't change all the cells, but you can look and look at the calculations and see that what drives capacity is almost totally the client choice. Because, like you said, single spring clients transfer data slower, and it takes a longer time for them to transfer the same amount of data. Thus, your capacity is driven by airtime. Airtime is shared between devices, and devices that don't talk very fast can't share very much. So that's kind of the crux of his whole thing. Yeah. Well, there's the 2 things I wanted to ask you. One, some controversial pieces that have been around in Twitter lately, specifically around minimum data rates. So you kind of talked a little bit about it. Tell us what you found from minimum data rates from your mentors.
Yeah, well, that's a very good one. That is somewhat controversial. Actually, the first thing about it isn't as controversial as 802.11b rates. And most of us as LAN professionals know that if we can disable 802.11b rates, that'll be great. Because one thing as I was doing my research, 802.11b is 17 years old. And I was mentioning to the people at Wi-Fi Trek, my daughter is now a senior in college, and she was in kindergarten when 802.11b came out. So it's a great technology then, but now it just really slows our network. So my first encouragement to the people at Wi-Fi Trek was disable, if you can, 802.11b rates, 1, 2, 5.5, and 11. You'll get rid of protection mechanism ripple, and it'll really help. Now, I know there are some people who have to support legacy clients. One of my mentors mentioned about a piece of multi-$1,000 medical equipment that he just received at his place of work. and the proprietary OS only supports 802.11b, and he's just crazy. He said, why couldn't they put good technology in this? I said, well, guess they didn't. So I'm going to say if you have to support 802.11b, maybe you can just support 11 or 5.5 megabits per second, and you can get by, at least eliminate 1 and 2. I think the real controversy comes when it comes to the OFDM rate, whether you can enable all those low, or whether you can disable the low data rates, mandatory of 6, 12, and leave 24 as a minimum basic rate, or if you have to leave all those enabled. And that's kind of where a little bit of controversy comes in.
And then we all have the 91836 issue as well.
Right, yeah. And several of my mentors mentioned that, yes, whatever you want to do, don't leave 18 as a minimum basic rate. Some of the older client drivers don't support 18, and they were going strictly by the standard, which says 6, 12, and 24 are the basic rates. And I said, whatever you do, don't leave 18 as a basic rate. So if you want to leave 6 or 12 or 24 as a minimum basic rate, that would be great. It's interesting that in some individuals who believe that you can leave all the 802.11b basic rates enabled, mention that because, well, they say that if you enable all the minimum basic rates, 6, 12, or if you don't, I should say, that you will get problems with FAR clients. They will not be able to hear that information. And there's not too many who actually believe you can disable or leave the lower rates disabled. I think if you disable the lower rates, you have a number of advantages. You help reduce the sticky client problem. You help with roaming. And you have really smaller cell sizes from the aspect that device has to have a stronger signal rate to connect to an access point. So it'll be able to roam more efficiently. So I just think that there's lots of advantages of disabling the low data rates. It just makes a much healthier, better contention domain all the way around. Well,
I will just have to comment. You said it kind of makes the cell size smaller, not from a contention domain. Contention size are still just as big as they ever were. It's just that roaming, hopefully they'll leave sooner because they can't have those supported rates anymore.
I'm going to say it doesn't. Yeah, we're not reducing the RF signal at all. We're just lowering those rates, disabling those lower rates, and so that client has to have a certain signal strength to be connected to an access point at a certain rate. When you disable those lower data rates, it then will look for another access point. That client will make that access point decision to connect to another device. So, yeah.
So how do we? What? After all of this discussion about data rates and your presentation, what do you recommend to your clients right now? The steps they can take to improve their networks?
Yeah. Well, yes. One of the first things you can do is, again, you can disable your lower data rates. I'm very firm with the fact that you can disable 6, 12. I've even heard some in high capacity situations where you can even leave 36 as a minimum basic rate if you have a high capacity, high area such as a stadium or a large auditorium. So that's one thing you definitely can do. Obviously, you have good channel reuse. Try to get as many of your clients from the 2.4 to the 5 gigahertz band so they can use many, many more channels, including our DFS channels. If you're not too far from an airport and you've checked that you don't have any issues with DFS, those are some areas that you can definitely look at. One thing that also one of my clients or my mentors mentioned, don't disable any of your MCS rates. That's kind of an untested type of thing to do. I think it could cause even issues with your network. So be sure that your MCS indices are all enabled. And again, use channel reuse. Try to use your channels, and if you can go to 40 megahertz channels, if you have a smaller area, that would be great. One-story office building, something of that nature. But probably even keeping your channel bonding to 20 megahertz, especially if you have a large facility, multi-story facility, or a large office building. It would be best to probably keep your data rates at 20 megahertz so that you have many more channels for reuse.
Well, we'll put in the show notes a link to your actual presentation. It's videotaped. Has yours been uploaded so far?
Yes, it has been.
Yay, good. And as well as you can get the PowerPoint, and we'll link both of those in the show notes. Glenn, how would someone find you other than through the show notes? Normally, how would they find you on Twitter or on the interwebs?
Okay. You can find me on Twitter at @grcate. And I have a Wi-Fi weblog at gcatewifi.wordpress.com.
And you have, how's it labeled? The ultimate weblog.
I try to keep as many new Wi-Fi blogs out there. I have a friend of mine just this week started a Wi-Fi blog, and I said, give me your link. I want to put it up there. So I've got a good handful of Wi-Fi blogs, and if you're a Wi-Fi blogger and you're not on there, please hit me up on Twitter or drop me a note on gcatewifi.wordpress.com, and I'll sure add you to the weblog link that I have.
I think that's a great service for the community, is to have, one, that you host them all, but two, anyone who has a blog, it helps not only yourself in your own learning, but by sharing your experiences helps others grow as well. So totally want to encourage as many people to blog as possible. Well, any final words on your data rates presentation? Anything you'd want to change if you had a chance to do it over again?
Well, no, not really, Keith. Here's one thing. I learned so much through the presentation on data rates, but I still have more questions. And so I'm going to keep doing research, reading through the 802.11 2016 standard. There is a lot.
400 pages of it.
3,523, I think there is. There's a lot in there. And there's a lot in there about data rates and how data rates are set. And it's a lot to do. So I want to do some more reading, some more research, and keep asking questions so I can learn more about data rates.
Well, I suggest you and others who want to try this, before adjusting anything to do with data rates, MCS, turning off minimum basic rates, etc., run a baseline, look at your current retry rate, your current average data rate that you're getting now, make the change, say from 6 to 12, let it run for another hour, or whatever time period you want to look, compare the retry rates, compare the CRCs, compare the average data rate, and if it's not climbing, if your average data rate doesn't jump, and it should jump considerably as you go from 6 to 12, again from 12 to 24. At some point, the average data rate will climb, but the retry rates will all of a sudden skyrocket. That will tell you pushed it a little too far. So back down a level, and then you found the sweet spot. So it's not just turn it and walk away. I think it's a test, baseline, test again, change one variable, see if it worked, and repeat. And eventually you'll be able to get a nice sweet spot for your site. It's not the same. You mentioned earlier some high-density places even have 48s or something going. So it depends on what works best for you. Well, thanks for your time, Glenn. We're glad you were able to join us, and thanks for your other podcast interviews and blog reviews you do for us. Glad you're part of the team.
Thanks so much, Keith. Appreciate it.
10 Talks.
So I appreciate with Rob, when I hear people talking about Claude Shannon, I know I'm actually in the right place. So it's a pleasure to be here. We're a little bit kind of a fish out of water comparatively to WLAN professionals. This is our first time joining one of these shows. Predominantly, as Keith was mentioning, when it comes to Wi-Fi, your Wi-Fi sucks all the time, because if Wi-Fi is not working, it sucks. And if your infrastructure that's slow supporting it sucks, you have a big problem, and consumers always just think it's your Wi-Fi and it's your fault. So I'm really here to talk more about where the future of the infrastructure side and the fixed access side is going. And to keep it more interesting also on your front, everything that I've been working on for the bulk of my last 20 years has been in the Wi-Fi industry and in the broadband industry in particular. So I started off in the Wi-Fi industry in probably 2000, building the first DSL Wi-Fi gateways, when we realized, oh my God, this is very difficult to support subscribers in homes, and now we need to have managed Wi-Fi gateways. So I was part of the team that invented the TR69 technology, which I know is a big piece of a lot of the controller market out there. So we had this vision a long time ago that we were going to get pervasive infrastructure and Wi-Fi would be there. And what I found over the last, 7-8 years is that as the promise of fiber getting delivered to the home, and everybody talking about how these next generation networks would continue, well, they actually have not continued as promised. And what we're now seeing is a big gap between the capability to deliver the speeds that both consumers and enterprise buildings, hotels, et cetera, need to be able to support Wi-Fi. So that's going to be the bulk of my talk today. And I spend a ton of time on looking 3, 4, 5 years out with chip technology and how we're driving our chip vendors to do the things that we need to improve quality. So I'm going to give you a view to what's happening in the next gen of Wi-Fi and also how we're taking advantage of these things in the fixed side. And some pretty exciting stuff, I think, that happened yesterday around 802.11ax. So I want to walk through that a little bit because I think there's a sooner reality than most think to some degree there. A little bit about Mimosa. We are very focused on what we call fiber fast wireless solutions. And of course, managing those things is critical. So of course, there's a lot of cloud technologies in that. I'm going to try to not go too much into too much detail about Mimosa here. It's going to be a little hard in some cases. We are kind of driving a very new direction of bringing fixed wireless into high density markets. That's never been done very successfully. It's really only been done in rural areas. So I apologize if I talk a little bit about what we are doing, but I think it is pretty interesting now to be able to bring high grade, high quality fixed wireless into urban and suburban areas that have never been able to be used for fixed wireless before, and it's where DSL and fiber typically have been and are falling off. We all know everybody wants bandwidth. There's a big separation as we're seeing between what you can do with a cellular network and where you can get Wi-Fi networks indoors in residential areas. And of course, really, if you want to do 4K streaming video and things that all of us Americans do all the time, which exactly is not representative of the rest of the world completely yet, but we think it will be, we need to have great fixed infrastructure. Really, the requirements that we look at, and driving out of Silicon Valley, of course, most of our partners that we deal with, they just come out and say, hey, look, I'm trying to turn up gigabit speeds with really low latency for augmented reality applications. Okay, well, that sounds great. Really, what people want when they get down to it is really low cost, 25 megabits to 100 megabits. Now, reality is we need to drive towards a gigabit, but the demand for gigabit isn't there. What we've seen, though, is every city out on the planet has said, oh my goodness, I've seen Google doing fiber. I've seen all these companies doing fiber. We must have fiber. And they don't even say I need a gigabit. They say I need fiber. Well, the reality is that obviously fiber is not the only way to get to a gigabit. And that's really what I want to talk about today is why is that and what are the technologies that are going to lead us into the next generation of how to get connectivity at much lower cost. And everything I'm going to talk about here today and the success factors have to do with cost of how we can deliver this into the ecosystem. So a little bit about fiber and why it is slowed down. The funny thing is we've seen DSL come to a crawl. ADSL, of course, is in negative decline. In fact, copper in general is in absolute tear out mode globally. But fiber is actually not growing as fast as people predicted 5 years ago, mostly due to economic conditions. And when on the low end, if you're really lucky, the best I've ever seen is about 700 euros to hit a household. Typically, it runs somewhere between 1,300 euros up to 2,000 to 3,000 euros, depending on what kinds of environment you're in. Rural, or if you can trench in the grounds and have right of way really easily. But this is obviously a really scary number to most people if you're looking at investing in new networks that are going to hit these great speeds. But think about developing markets. Think about places that have no infrastructure in buildings. In the United States, as an example, 80% of people live in cities and suburban areas. So all this time we focused on wireless in rural areas. There's more underconnected people in cities and suburban areas. Now looking globally, looking at Middle East and Africa, Southeast Asia, it's about 60% of people live in suburban areas and city areas. So it's very clear we've focused the wrong way where we're trying to put very expensive technology into very low cost, low infrastructure regions. And that's why fiber hasn't been the best match except for the best tech cities available in the world. So you look at Singapore, you look at Hong Kong, you look at Tokyo. These are places that started early and had a thriving demand and the socioeconomic conditions to drive that. So what do I look at? I look at really a fiber solution that is actually more of a partnership between wireless and fiber. Fiber is as deep as it makes sense economically, and it's going to make sense in every market very differently. Then we have to have different solutions based on distance and density and technology and spectrum available, of course, to go the next route. So I touched on rural technology a little bit. Rural, it kind of inspired us to get into this business. We saw this thriving wireless ISP, the WISP community that people have talked about over the last 10 years. And it started in rural areas where there was no connectivity. And what we're seeing is there's been zero crossover between places where there's fixed wireless with places there's competition with DSL and fiber and cable. And the reason for that is people really were fine with 2 to 3 megabits with wireless as an internet service because they had nothing other than a modem otherwise. So now what we're seeing is that tech that was used in rural areas at long distance on towers, and it was very difficult to find channels to use. You found self-interference everywhere as you tried to put up new sectors, add more subscribers. It was very not scalable, which is why we've never been able to go into suburban areas. So what I've seen more recently is a huge drop-off in the speed at which cable guys are upgrading their networks to DOCSIS 3.1. And there's huge costs to do those upgrades, so they only want to go after their best markets. And obviously in the DSL communities, you're actually also seeing a drop-off, of course, because you now only can really get hundreds of megabits if you're at about 100 to 200 meters away from the subscriber, and you have to drive fiber all the way that deep, and you then have to troubleshoot the ancient copper that's still in the ground that's causing all of these problems that people have in deployments. So, when we look at the opportunities, and, the funny thing that we see is the world is not structured the right way. Cellular guys have a ton of money. They're going to put it into cellular spectrum. We're going to talk a little bit about 5G and what's happening there in a little bit. But the overlap of guys to go off and deliver new bandwidth in these towns, it's really actually not the cellular guys that have the best interest to go do this. In fact, in many cases, it's independent, larger operators that are coming into the market that have capital that can seize an opportunity that's a much lower cost opportunity than doing licensed spectrum. So that's really what we're going to talk about today is how can we coexist both unlicensed and some lightly low-cost bands to make fixed internet a much better place and much better technologies, and get this into markets where there's a mass underserving of the technology and availability of the technology. So let's talk a little bit about LTE. LTE, as we know it today, is really a technology that is tower-based. And the challenges that we run into with this, of course, as we get into cities, we start to oversubscribe. So then started this whole thing that we all know called small cell. And small cell, of course, has had tons of difficulty getting off the ground for a lot of different reasons. It came out in the advent as people started talking about 5G, and the whole world of small cell is relatively on install mode globally as people are waiting to see what the next steps are in 5G. So we think that there's challenges in both models. We see in rural areas, and remember back to my previous slide, rural areas don't need that much and there's no competition. And there's also not a lot of capacity overage in rural areas. So it's actually okay to use 4G in rural areas to compete with the little wireless ISPs. 10 to 20 megabit service is going to be really, really good for people in rural areas. And the wireless ISPs are struggling to jump up to the next level in rural areas to get ready for this competition with LTE in those markets. But if you think about in cities, macro cells in cities are totally overrun right now. You could never put 4K video or any of these kinds of applications we're talking about onto the cellular network at scale and expect it to continue to thrive. So moving on to small cell, if you look at what's happened in the last 6 months, so great example, when we started the company about 4.5 years ago, people thought we were crazy. First of all, nobody invests in wireless companies right now. Nobody invests in hardware. Telecom, 0 for 3. So what's happening now 4 years later is the whole world is coming around to the concept that fiber can't afford to deliver. Then there's plenty of spectrum and technologies that get the speeds that we need. So the 5G market about 3-4 months ago started completely spinning their story away from mobility and away from IoT and saying, oh yeah, 5G is actually going to be all about fixed internet. But the reality is they're pushing that story into millimeter wave bands. So that's 60 gig, 28 gigahertz, 39 gigahertz, and up into 70, 80 gigahertz. And there's a little bit of a rotten story here, because if you do the math, you do the physics, you know that if you put this technology in any typical suburban area, any one of those frequencies that hits a leaf on a tree is never going to let the signal propagate. And you'll see tons of stories out there in universities that have gone out and said, 5G will work at 200 meters with no trees. Okay, so read the studies very carefully, and now you'll understand why we focus on sub 6 gigahertz for the last mile. And it's not just about using 5 gigahertz technology. This technology is a platform. It's an architecture that needs to also embrace all spectrum that makes sense for fixed. We, of course, believe in trying to keep Wi-Fi spectrum as free as we can in many different ways, because the last thing we want to do is occupy this really precious resource that we have. So I'll keep that to that part of that discussion to that, and I'm happy to take questions on other pieces of spectrum after the talk. So let's talk a little bit about what Google's done. Google started in the U.S. working on fiber in Kansas City, and it was heralded as the next direction. I think many of the European operators that I worked with at my last company, it was all moving towards fiber. I'm actually a reformed fiber guy at the end of the day. I was building out AT&T Uverse with AT&T. And what I saw with this was, well, no matter how you slice it, in suburban areas, and unless you're doing large MDUs and can find ways to wire them from the ground up, it doesn't make sense cost-wise. And the Google guys got that finally. So a couple things they did. They started making these announcements that they're slowing down their fiber rollouts, and then they went off and bought a wireless ISP. In fact, it was funny because it was my ISP in my building in downtown San Francisco, because I've been getting fixed wireless 100 megabit, and if you want to pay for it, you can get full gigabit services. But I pay about $45 US a month for 100 megabits, which in the United States is amazing. That's something that the cable guys are scared to death of, and that model, it's very clear that model scales. Nobody knows where they're going next. Only Google knows that. But it's very logical that now that they've looked at solving the apartment building problem and the larger buildings in your neighborhood, now how do you solve the suburban areas, which is where they were taking fiber previously? So this is really, I think, where the answer is going to lie on a more global scale, is how do I move into suburban areas next? So talking a little bit more about 5G, it really was funny to us to see the comments that Verizon came out with about 4 or 5 months ago saying, this is amazing. They started doing these field trials in Texas and said, okay, this is great. We have 30 homes that we've lit up with all of this technology, and it's working perfectly. Of course, these are perfect conditions, line of sight. It's telling them everything they want to do, with the disclaimer, well, the CPE is about $800 just for the wireless equipment. And that's because it's these really high spectrum that is really not low cost RF technology yet. So the front ends don't exist yet, and blah, blah, blah. It's not there. The reality, though, is they did get one part right, which is if you can get to within 1,000 meters, probably 500 meters, you're in the sweet spot for fixed wireless technologies, where previously you were trying to do 6 kilometers, 7 kilometers, 8 kilometers. So we're going to flip this architecture upside down. Okay, so that's all the kind of market talk. I'm going to get into the technology now a little bit. So I'm going to talk about what we see the key architecture pieces, components being, and how do we build something scalable for neighborhoods, et cetera. First, of course, it starts off with MIMO technology and massive MIMO technology. Now, the term massive MIMO is starting to get misused. We started off in this space when massive MIMO was 4 streams of MIMO. And then you start hearing of these rumors, and Rob said it great earlier about what's happening with multi-user MIMO. And wow, that sounds like a great marketing thing. But the reality is nobody's getting the efficiency due to the overhead and the overhead of the airtime, and also the math inside of the processor that has to do all of this smart stuff. So we've all run into it as an industry, a problem of, hey, now we can get lots of MIMO streams, and that's really cool. But I did not get, as I added 2, then 4, then now 8 streams of MIMO, did I get 4 times the capacity doing that? Well, no, because it's not that efficient. So now we're hitting the realities of what some of these technologies are capable of, and the antenna techniques and stuff like that goes with it. Our evidence shows that to get really the kind of scale where you can get like 25 clients all being simultaneously downstream to, you'd have to have an array of 128 antennas to make that happen. And that's extraordinarily expensive to do that. So we think that it's going to take a piece of this, but a whole bunch of other things to get there to get to scale. The next piece is what you all know in the Wi-Fi space. CSMA is like the enabler of everything we've done, but it's also a horrible, horrible beast that causes all the problems that we know about. But it brings forward, of course, everything that we've had from a product compatibility, the smartphone market, and that's great. Well, in the fixed wireless space, I get to deviate from that a bit. And I can solve a lot of the problems of the inefficiencies of MAC layers as I get to higher client counts, and start to solve issues that come up as it relates to client count going up and very high burst speeds of people trying to use the network. It coincides with another concept, though, which is spectrum reuse. And we have never really come up with a way to do spectrum reuse very effectively. Now, we started working a couple years ago starting to get our gear into the market in the point-to-point space. And I think that, a lot of people that realize I can't always get my Wi-Fi APs where I need them, especially when they're doing outdoor events and I need to get access points in the middle of a park, you typically bring in something to do point-to-point. We started demonstrating this technology to show that I could really reuse the same channel over and over again in different directionalities and at both a single location and across the network. And we very successfully did that in the point-to-point space. So now the hard thing is, how do I build a network across an entire neighborhood or an entire city trying to reuse one channel? Well, it sounds a lot like mesh. But mesh has its own problems. So what I want to come up with here is a technology solution that does not cause self-interference, but that is not dependent upon one access point taking a radar hit in the DFS band and everything falls apart. So this is really a hybrid architecture of getting good backhaul that's really not mesh technology, because now you're dealing with probably 5 to 10 gigabits coming into neighborhoods needing to get backhauled out. And now localized radios that do not cause self-interference between the clients and the access points between each cell node. And that's actually what is being worked on with that technology. So I don't have to be a hog, as the traditional wireless ISP, I think, has been in some areas, where to add another 30 subscribers, they added another channel. And I couldn't use that channel anywhere else because it radiated so far. And that's completely foreign to what we believe in, which is spectrum reuse is critical here. And then we deal with what you guys already know about, which is the controller space. How do I make sure that when I do have noise problems and channel problems, how do I gracefully deal with those issues, both at the AP side that's responsible for many devices connecting, and each unique site that really runs into a problem that desperately needs you to mitigate that? And how can we use machine learning to do that quickly and move a client into a better state, whether that is masking channels to smaller channels, and some future tech I'll talk about in a little bit. But this is where the cloud is the only thing that can work. Our brains, I really strongly believe in not doing auto channel and multi-point. Very, very much is what I think you heard a little bit earlier. For a lot of reasons, you have a lot of customers on a particular access point. You don't want them to be jumping around. And you have a lot of other access points. So it's kind of, when one moves, you have an amorphous blob that you're dealing with through that whole process. And that's why we fundamentally believe that we can take each access point carefully and also adjust clients to be able to make their performance work better under noise conditions. Okay, so let's talk about massive MIMO and kind of getting deeper into this topic. So today, as we know it, shipping in the field, the largest count that we see out there is in commercial products. I'm going to differentiate this from the stuff you read about Facebook doing with 27 antenna technology that's very, very expensive at long range. The best thing about Wi-Fi, of course, has been it drove this low-cost basis, and it's also driving technology at an incredible rate. I mean, it was only a couple of years ago we were really still at 2x2 and 3x3, and we're now on the advent of very, very low-cost 8x8 with multi-user MIMO. But as I was mentioning earlier, he said multi-user MIMO doesn't work that well yet. So we're going to talk about that in just a second, how we think that we can use that dimensionality in other ways. And what we're starting to see is that the technologies behind Wi-Fi and LTE are starting to collide. So if you look at the core technologies of wireless, we'd all kind of agree from a physics and a client organization and a scaling perspective, LTE kind of got that right. What they didn't have right was building products that work in the presence of interference, and they only work in licensed bands, and that's causing everybody an issue, and that technology is very high cost. The base stations can be hundreds of thousands of dollars, and then small cells can be $4,000 or $5,000 in a lot of cases. That's way more expensive than what Wi-Fi gear costs, and that's really the challenge here. What we are seeing, however, though, is a segregation, and this has been a big issue for vendors in this space across the industry in Wi-Fi. The chip vendors don't necessarily believe that they need to have better technology in the access point chip than they do in the client. And this symmetry between client and access point chip has been a huge disaster in this industry, in my opinion, because the chip vendors want to get into every mobile phone and laptop, and they really don't care about what kinds of integration you can do inside the access points. Take it one step further, the FCC in the US is really preventing people from putting open source code on routers because they're concerned that people are hacking the routers. So we're now in a situation where you have very little control over the chip. You have very little support to make changes to a router anymore, and that's being driven from one of the most influential policymakers on the planet that way. So what we saw early on when we got into the space, there would be an asymmetry coming soon to clients and base stations, and that people that focused on high-performance base stations would be rewarded by the infrastructure market, and people that focus on low-end 1, 2-stream MIMO devices would be rewarded probably in the smartphone market at much lower margins. So we really focused on the higher-end piece of that and made sure that we could take advantage of the low-end client and have a very high-quality base station technology. We started early by partnering with a company called Quantenna. Most of you probably have heard the name, but they have not actually really shipped into the traditional Wi-Fi space because they were so dead focused on delivering media through the house, which I find is funny, as Rob was mentioning earlier, the old adapter market. You know, that was the first place a lot of us started with Wi-Fi, was how do I get media from the set-top box to an adapter over here and make that work? Well, that technology is actually the best Wi-Fi technology out there, but it didn't have all of the enterprise bells and whistles that are needed for roaming and all the rest of that stuff that goes with it. So what was announced yesterday was really pretty amazing. It's something I've been working on for 4 years to drive, is really getting the first availability of 11AX silicon, which is coming out in the early parts of 2017. We're already playing with it internally, but it's really astonishing. We're now seeing literally 12 MIMO streams on a chip at just incredibly low costs. But it's not the MIMO streams to me that actually matter so much. It's really what technologies that we're getting along with it and what problems they're going to solve. So the first big change that has happened is the Wi-Fi industry has clearly recognized that multi-user MIMO is not always the best way to go because it's very complicated to make work, spatially, compute-wise, airtime-wise. So OFDMA is the new king. It's not really new because we've been doing it in cellular for a few years now. But I think what you're going to see is very, very low-cost devices that now get this incredible technology to be able to basically give subcarriers to every client and coordinate clients. So we're getting into a world where even the standard is moving towards coordination of both spectrum and time, which is really, really good. So getting these dedicated subcarriers per client is going to be huge for this industry. Now, I'm going to caveat this by saying, hey, we may all get products out, and I'm not even talking about to the Wi-Fi industry getting this out early next year. This is still going to be, you know, you'll see APs coming out at CES, I'm sure this year. You'll see probably 15 of them with 12 little antenna sticks coming off the back. And they're going to be draft ready, and that's not my business, so to speak. But how long is it going to take for this tech to get into the smartphones is all that's going to matter for this business. My guess, starting in 2 years, and it's going to be just like the U.S., where we're 100% 5 gig now because we're the first people that move to these new devices, and then probably 2 to 5 years down the pipeline, we'll start to see that seep into the developing markets. And this is kind of the game that we all have to play with, is we got to get started at some point and then move that down the wire. The biggest thing for the outdoor space, which is the biggest thing for my space is really, though, is dealing with outdoor interference at distance. We'll talk about distances in a minute, but moving into smaller subcarrier spacing and also better cyclic prefixes, this is really big for to make links more stable in the outdoor world. And they tried to take this kind of high efficiency and reliability into the new standard. Now, the things that didn't really get in, because they're different concepts, and also take a more dedicated client with this technology in them, are things I was talking about earlier, GPS sync. So now if I can apply GPS sync to a lot of these other concepts in a fixed environment where the client and the access point are controlled together, you can do some incredible things by not only reusing the same channel up and down the street, up and down the neighborhood, but each one of them can then also make its subcarrier decisions on a per-user basis. The other thing I really love technologically is something we call OFDM tone mapping. And that's something that allows me, especially if I'm syncing, I'm now taking up fewer channels. So I can use a bigger channel, and I can now spread that out in different OFDM tones to different users. And every client can tell me what their noise conditions look like. So it's a little bit like a channel state sounding for multi-user MIMO, but the noise conditions don't change every second versus a handset moving down the street because you're fixed. So I can keep track of every client's noise condition and mask them out in non-adjacent tones and give you the best spectrum for you to listen on which is something I think is going to be huge, both at the receiver of the client and at the access point. And it's going to allow, when combined with spectrum reuse technologies, an incredible performance under interference and also friendly performance, because now every device is not only listening, it's listening with a finite detail level of OFDM masks. And that's something that's going to, I think, be a big, big differentiator for this market space. So this is kind of the feature set, so to speak, that we're driving towards. We dreamed up a lot of this, about 3-4 years ago when we started the company, and pushed the chip manufacturers toward this. Quantenna was the only guys that listened to us because they didn't have a legacy business in this space, and they wanted to see that get developed. I think that what we're seeing is that the separation between base station chip and client chip has happened now. And this is really, truly getting over the edge, because not a lot of people want to chase up in this direction. I'm excited for this room of people because I really hope that they can see that technology adapt more into the WLAN space, where they haven't been as much of a player. But that's something I think now that they can start that process, because it's so highly differentiated to get that done. Okay, so I'm going to turn to a little bit to kind of how do I actualize this, and I want to show exactly what this new architecture looks like from an RF perspective, link budget, and kind of key features, and what are we trying to do. And it's something that we call a micro pop, or a micro point of presence. It's not a new name, so to speak. Some of you may have heard of it before, but it's really, the concept is to get very, very close to the subscriber and really get overlapping coverage zones for being able to give many different places to aim antennas at, and get huge, what I call geocapacity into an area. So the first goal here is keep everything under 500 meters to the houses you're trying to service. And what we've seen is that this makes perfect sense for town areas that are larger than around 400 households per square kilometer. And you'll have to go to Wikipedia and look at examples of your different towns, so to speak, to know what those are. And that ranges up to about 1,000 homes per square kilometer. So in the U.S., for me, as a good example, I can look at towns like Austin, Texas, where Google went after fiber with, and that's about 400 homes per square, households per square kilometer. And I go to a place like San Francisco, and it's 2,000. And that's because it's multi-dwelling units. So there's it's not an appropriate architecture going into cities, which is more of an MDU style architecture. So that it really is targeting these single family home, small multi-dwelling environments, and distributed home environments. The architecture, unlike mesh, of course, this is very backhaul dependent. So we have to work with a lot of different companies that are both delivering fiber into neighborhoods and try to put these base stations or micropops wherever you get the fiber conveniently. And in many cases, we need to develop our access point locations based on where we can do line of sight backhaul to. So that millimeter wave thing I was talking about earlier about being so terrible for 5G, it's not so terrible for point to point. In fact, it's incredibly good at about 500 meters. So if I can get line of sight and get a constellation of access points using that technology, it's a huge deal. So we believe it's a combination of backhaul, millimeter wave, licensed in some cases in different countries where it's cost effective, and then fiber fed, of course. So today what we're seeing is around, rock solid speeds of around 250 megabits with a 4x4 architecture. And this is shared across, a client range of about, let's put it at 15 to 30 clients per AP. It's very different than the rural side where you're trying to put a whole bunch of access points on a tower. The same concepts actually work, and that's other work that we have tried. But generally speaking, this is about the target that we want to get to for bursting speeds. And then when you hit capacities, you want to, we're seeing that you're able to still reserve 50 megabits guaranteed for people when everybody's streaming video at night. So it gives you great speed test results, and it gives you really a very nice sustained speed in that process. And then, of course, GPS sync, so all of these nodes can overlap. And the only risk that you have, which we'll talk about more about interference management, is an individual client aimed between multiple different access point coverage areas. So at the throat of the access point, as I like to call it, that's the only risk that you have. And then we have to mitigate what kind of interference happens during that. And reality says is that I only need to be 10 dB down to be able to tell the difference between a client I was expecting and a client that I wasn't expecting. And that's working incredibly well, especially when you have a little bit of foliage, because it really drops the signals down. or if you're just far enough away, you lose 10 dB very, very quickly in this world. So it's been fascinating to see the success that we're seeing in these kinds of distances because you're using directional client antennas and more 360-degree coverage areas. They are not omnis. I'm going to talk about that in a little bit. I don't recommend omnis to any of my best friends, but we've kind of redesigned some technologies around the antenna, which we'll step on. So where do I think this is going to make sense? Anytime you see fiber more than 1,000 or so euros per household, it makes sense. Any place where you see LTE is being over capacity, it makes sense as long as the customer doesn't already have fiber. In markets that have not moved from ADSL to VDSL, it makes perfect sense. There's a lot of markets that do this. We actually have done a lot of geo-data analytics on this to kind of identify percentage parts of countries and around the world about where these dynamics make sense. Where the dynamics make actually really interesting sense is in developing markets, apartment buildings, where they don't have any kind of copper or Ethernet or fiber ability up and down the risers in the apartment building, and they need to get signals through the windows. That's actually another option for this market, which puts it into the much higher density market space. So we are seeing that is a very good potential option. It's very, very low cost and can be self-installable. So that's something that we see as very unique and interesting. Looking at ROI, which is kind of the most important thing, roughly speaking, in any architecture that we've seen, it comes down to about 200 euros to 300 euros per household of capital expenditure. By my count, that's roughly a third to a fourth of the cost of any type of fiber. And as you drive into self-installation models, that goes much, much further down from there. So it's really an interesting payback. This is kind of a next generation of a new kind of wireless ISP industry. The wireless ISP industry had been very, very profitable doing what they do in small scale. So how do we do that in larger scale technologically at this point? The other piece that I really like is it's a really, really interesting overlap both with municipalities harkening back to the old municipal Wi-Fi days and their problems in their cities. So the problems that cities always tell us are, well, we don't have competition against the big guys, and they're not doing what we asked them to do. They're only going to go after the markets that make sense, not necessarily the underserviced areas of town. Second, they say, I want Wi-Fi everywhere. How can I do that? Every Wi-Fi conference I go to, there's always a panel discussion about monetizing free Wi-Fi. And we know that doesn't work. It's great advertising, and the problem is the cost to put out free across an entire city doesn't make sense. But if somebody is putting up competitive broadband throughout the city, it's a very good partnership to work with the city to put up Wi-Fi at the same time. We've actually packaged it together to make that easier inside of the same container, so to speak, as you can kind of see up on a pole there in the little tube, not the giant thing on the left. That's kind of some old Wi-Fi gear. But that makes it a lot easier to start to put that out across neighborhoods. So now you can do both Wi-Fi for the kind of local area outdoors and then fixed internet to homes to get that done. It's also, of course, at that point, if you get in well with a city, and what we're talking about now is what we call public-private partnerships. These are things where you're going to get advantageous pole attach rates because you can get you're going to be giving the city services at the prices that make sense for them. And the ones that most important for them are actually what we call the homework gap, or connecting up students that can't afford broadband or their parents can't afford it. And now in the U.S., most of our schools now, for example, they don't have apps to submit your homework, but they have to submit their homework on their laptop. And to have laptops, they have to have broadband. That means they have to go to the library to turn in their homework now every day. So there's actually a ton of funding to make those projects happen. When you combine these together, it is a win-win for both the ISP and a city. And that's something I think that is pretty unique. So talking about antennas, we realized there was some pretty interesting things a couple years ago as we looked at the deep technological regulations around antennas. And in particular, we found a couple of things. There's some really interesting rules around circular polarization that if you directionally put circular polarized antennas, you put out a different stream in each direction, you get an extra 3 dB. So we went this path because it gave us much better signal, but also because we were realizing that if I can group clients in different directions, I no longer need to think about the channel state information for things like multi-user MIMO and OFDMA. I know they exist in that quadrant, that quadrant, that quadrant, or the fourth quadrant. And that's a very easy grouping now for these directional clients to do this. So we're flipping upside down the traditional logic of I put 4 stick antennas in the same direction and I kind of blob some energy that way. And then, there's obviously beam steering technologies that have evolved to do kind of similar things, but this is 4 live antennas, so to speak, and eventually moving to things like 8 live antennas in these different directions. And this helps us group our clients for faster math on the processors so that we can start to slice up not only time, but spatial diversity and soon frequency diversity with OFDMA. I think this has been a unique approach to kind of do something very, very different. And that's why I said this isn't an Omni. It's really not blurring and blasting information in every direction. It smartly only sends where it needs to and listens only where it needs to. And I think that's a huge difference. Let's talk about link budget for a second. So I use examples here in the international power levels in the DFS band. So really, if you look at kind of the 300 meter marker, what we're looking at is around minus 44 SNR of 31 dB to get to MCS9. And that really is going to render out. If you were the only client on the network, great, you're going to get 600 megabits, but we don't think that way. We have to average that out across a user base and also users that are going to be slower, further away, and lower signal. So you're going to see as you move further out at like 600 meters, you're down to about MCS6. And as I move down to 80 megahertz, 2 stream clients here, of course, the 2 stream clients are down to about, in line of sight, you're down to about MCS5. The cool thing with this, if you throw some trees in the middle, you've still got some headroom, which is really nice. So really, I don't need that much to keep up service. And, the impacts to cell size, I mean, what we learned about the Wi-Fi chips, as we call them, are too good listeners. They were designed to be so good listening to absolutely everything. It's what kills Wi-Fi. So we had to take a step back and say, how are we going to detune Wi-Fi so that it actually intentionally does not listen as well to everything else? And I know that sounds absolutely ridiculous, but that's the reality of Wi-Fi chips. And this is what you have to do something from a resiliency perspective. None of this applies to smartphones. This is all about fixed internet. So we could take these liberties to make these things work because we knew what we were supposed to be expecting. So really, things like automatic gain control, which we'll talk about in a second, this is stuff that lets us use spectrum that looks really bad and actually make service work really, really well. This is what shocked people that have started using this was they had full expectation of failure in a certain environment, and as they get these good signals and have these techniques, and we've put it so that you don't try to listen so strongly, it works magically. It's a very, very different situation. So the key to this is actually doing automatic gain control. How many people here know what AGC is? I hope everybody. Wow, not so many. So really what this is really trying to identify and eliminate short preamble failures. So the goal here is I need to be 10 dB of signal above noise, and that gets me what I need to deliver service. So you're squelching in the old radio terms and on the old ham radio kind of terms out the noise and avoiding short preamble fails in that sense. It also make sure that when we have trees and houses and things in the way, as I add in outdoor Wi-Fi of my own, which should be self-interference, that I'm going to be 10 dB down from the next cell over in almost any certain circumstance. And when I have Wi-Fi routers indoors, they're always muffled by their own home noise. So what we've seen is zero impact to the home Wi-Fi, even if it's on the same channel as the client on the rooftop, because 1, it's directional, and 2, the house is very well insulated from 5 gigahertz. So again, 5 gigahertz really good because it doesn't propagate as far from an indoor perspective outdoors. So it's a very clean environment in many cases. This differs, of course, depending on how much Wi-Fi hotspot you have up and down the streets from an interference perspective, but this gives us a really, really good architecture to go with. The next piece we had to really look at is, okay, how do I very simply make it easy for an installer, let's say like a satellite dude that installs satellites every day? You want it to be as absolutely easy as possible and give them multiple different aiming opportunities. So now I'm really close to a whole bunch of constellations of access points. So really, it's just let's get modern and let's build things like apps into the ecosystem of the installer and give you the targets that you're supposed to have when you do these installations. And these are the things I think that are really going to help this market grow quite a bit. So lastly, I'm going to leave here with a little bit on real-world deployments. You can see this example here is in a very dense treed environment. This is in Minneapolis in the United States. This particular company has a whole series of utility pole rights up and down the city, and they put them on every street corner, which causes, of course, as you can see, puts you right into the tree coverage. So the goal here was to make sure you could get all the way to the other side of the block, but mid-block is about as far as you really want to go before the other access point on the other side can start feeding the other side and directionally aim the antennas in the right direction. So it's pretty phenomenal when you start to look at these distances. They match up with the house densities now. So it actually, even though you're putting a ton of access points out there, the revenue opportunities for an ISP are there because the propagation distance is now about equal to what you need from a service perspective. If you're trying to go for, let's say, 30 to 50% of the population getting your broadband, that's what this looks like. This is a little bit more suburban. Another ISP that started doing this model. And, you can see they put in 4 access points and you can see the distances between them. And they used products from in the 24 gigahertz and in the 60 gigahertz to do backhaul between them. We have a few guys trying to do 5 gigahertz backhaul, but they want to keep the rest of the band, of course, for Wi-Fi and other applications in the neighborhood, and of course the fixed broadband. But it's actually a pretty straightforward architecture. The hardest thing is you actually have to find the right place for backhaul, not for where to put the access point. So the access point needs to go to the best place for backhaul as opposed to the best place for coverage. And you'll start to see that architecture becomes quite a bit different as a result. They were working, in their case, on 80 megahertz channels, and they were trying to go to 30 clients per access point. So you could see they're a little bit more spread. So they're probably going after about 20 to 30% market share in this architecture. And if they want to go deeper, they would start dropping more access points in, potentially lower the power if they need to. But they're typically hitting 30 megabits client burstable. They try to do 25 megabit client sustained during the peak video watching hours. So this is really, kind of what they look at from an economics perspective as an ISP trying to do this. Last example I'll show here is an ISP in the Chicago suburban area. So very dense suburban area, trees everywhere. And, they went into an area for the first time that I know of with an ISP competing with one of the bigger cable companies. And they're cleaning up clients because of the hatred of cable and in most cases the speed of cable because they haven't upgraded the further suburban areas into DOCSIS 3.1. There's a big advantage for them to go off and do that. So they've really focused on really pushing peak speeds in their neighborhood. This is a speed test that they ran. It's really pretty incredible how now we rethink the architecture, we rethink the RF, we rethink the MAC layer, we rethink spectrum reuse from the ground up. We have a completely different approach and technique to that at that point. So, while I know many of you guys are on the WLAN side, you do have infrastructure problems in getting bandwidth where you need it sometimes. So hopefully this has been a good education on kind of what's happening in the industry wrapping around you and what may be coming soon from a chip technology perspective in the WLAN space. If you want to learn more and kind of look at how these signal level plans and how the kind of population density plans work, we actually do have free tools for helping understand and design these kinds of things up on our website. So those are completely free to use, and that also has all of the point-to-point link planning as well. So those are, don't like to say it, but my users do, but it's probably the best link planning tool in the industry if you need to do point-to-point and estimating the kinds of speeds that you need in interference and channel sizes and antenna design, et cetera. So if you'd like, feel free to go take a look at that kind of stuff. Oh, no, sorry. On through there. And with that, that's everything I had for you today. So take any questions.
I'll start, since I have the mic, I'll have the first question. Use some terms that they might know, unlicensed versus lightly licensed versus heavy. So can you describe the range of the licensing frequencies? Great question. And the answer... And then I'll pass off the mic to whoever's...
So I'll use a couple of examples. So let's use the E-band or the 70 gigahertz. So people that are looking for 1 kilometer backhaul reliably. So in the United States, that's what we call a lightly licensed band. You get effectively a national right to use at a very, very low cost, and you can put in your links, and you just need to register the links. But there's no coordination efforts. There's other, if you look back at the old 3.65 gig band, that was also lightly licensed, meaning that you got effectively a national license and you weren't paying per link. Then you have fully licensed, which is what we call the traditional microwave, 11 gigahertz, 17, 18 gigahertz, 23 gigahertz. And those can be either very low cost in some countries, and in Europe, they're typically very expensive because you pay by the megabit, so to speak. So that would be my definition of the different ones based on the licensing type.
Thank you for joining us for another episode of the Wireless LAN Professionals Podcast, the podcast for wireless LAN professionals by wireless LAN professionals. Be sure to follow us on Twitter at Wireless LAN Pros for all the latest news and updates, and also connect directly with Keith on Twitter at Keith R. Parsons. Head over to www.wlanpros.com for this episode's show notes, as well as the latest in all things Wi-Fi.